dissipate all that energy in one spot, it could be potentially really dangerous, or it could potentially scour out the bottom of the bridge or the dam abutment. So that's always a concern for the engineers. They're always worried about something called piping, and that's where you get water that starts to erode the footings of the bridge or the structures and starts transporting the grout and other material that's used to place the boulders in place, and you can eventually have collapse of the whole structure. So at any sort of civil engineering project, you're always worried about that. Any sort of piping like that is going to be real bad for the structure long term. So in your modeling, we're not going to ask you guys to simulate 4 different structures or 4 different features. The engineers have a couple of different designs that they're going to use for these center features, which are going to be catering more towards whitewater kayaking. But what we thought would be interesting, because it's largely unproven in the mathematical modeling world, is what goes into making a wave, which is what we're proposing to have at the top feature. So waves are really difficult to model for a lot of different reasons, both physically and in the virtual world. There's some really powerful software out there that allows the engineers to plug in a lot of parameters and to try to come to some sort of understanding of what these features are going to look like, but they're only as good as the data that's put into them. They're only as good as to what degree of accuracy they can mimic the conditions that are going to exist in the channel. There are also challenges with physical modeling. So you guys are basically being tasked to come up with a physical model that's going to display what we might see in the channel. It's a great challenge because it's working on a lot of esoteric principles. We've got water viscosity, we have hydraulic flow and pressure, we have the interaction between the gradient, the channel shape, the downstream pool. There are just so many parameters there that you can influence, and you can come up with a whole host of different shapes of waves in the river based upon those parameters. I'm going to just show you guys a few pictures that I came across on the internet that over the last couple of years that show some of our different potential wave shapes here. And so, switch over.
I had to push it hard. There it goes.
This is a wave in Munich, Germany. This is obviously during Oktoberfest. So this is a wave on the Ottawa River. You can imagine with a lot of flow, like we have on huge river systems like the Ottawa, you can get some pretty enormous waves. This allows, when you get enough water velocity, this is a wave on the Zambezi River. So if you want to talk about wave quality, this is kind of what you guys expect to see. That would be pretty amazing to build into the chutes, because we're going to be working with about 1,000 CFS. This is about half that flow, about 500 CFS at a whitewater surf park in Colorado. So this was built over the last few years. You can see a few of the grounded-in structures here. This wave shows what we would call a large foam pile. It's obviously, again, in a really large river system. I'm not sure exactly where that one was taken. And again, real large river systems allow for a really high quality experience because you have a lot of water velocity coming in this way. You have an invert. This is the low spot where the water coming from above drops in and then comes back upstream. Again, you can see these really large river systems allow for a really amazing whitewater and surf experience. We're going to be dealing with a very limited flow, so what we're going to ask you guys to do in your model is to basically make use of a relative scale based upon the amount of flow that we have. So, yeah.
What did you say the flow was?
The flow is going to be 1,000 CFS roughly.
What is the scaled CFS?
I'm not sure, Gavin, what the exact scale is going to be.
I don't know either about the.
Yeah, I think it's going to be on the order of a fraction of a CFS. Here's that same wave in Munich. So this is kind of a good example of an artificial spot that's being produced on less than 1,000 CFS. That's about 600 CFS, and this is the same spot. This is called the ice spot, pretty famous spot. EISBACH, if you guys want to look that up online. It's a pretty famous surf spot in downtown Munich, Germany. And here again are our Oktoberfest participants out there surfing on the ice block wave. So this one I thought was kind of interesting because it represents roughly the same amount of water we might see, or even less, than in our wave park here in Bend, and it's going to provide some inspiration perhaps for what you guys might want to build. So this is kind of another example of a great wave. You can see here the invert, the water coming down, the below pool depth water here, then coming back up to the pool depth. And then that kind of shows how a lot of these waveforms are built. So in general, we're almost through here. In general, what you have is water coming from above, flowing down, going below the pool depth and coming back up. You can see this water here is below the pool depth behind it. This is another wave in downtown Munich. I've actually surfed this wave. It's really, really fun. And here's another great example of a nice wave where you can see there's the invert and then the wave height. So basically what we're trying to do is we're trying to make the most use of the available kinetic energy, the energy that's being produced by the water flowing downstream. And we're trying to amplify that wave height behind the invert as much as possible. And that's the great challenge in wave construction, is how to get the most height and therefore the most quality, the most wave surface, the face of the wave as tall and as broad as possible using the amount of energy that we have in the system. So for you guys' information, the amount of energy, or the amount of drop that's going to be dedicated to this primary feature, the first wave in this series, is going to be about 2.5 to 3 feet. Doesn't sound like a whole lot of drop, but when you have 1,000 CFS dropping 2 to 3 feet, there are several tricks you can do to make the water flow faster and therefore give you the opportunity to create the biggest and tallest wave. So the slide shows just about through. Here's another whitewater park in Houston, Texas. This one flows only rarely, but you can kind of see some of the different features that have been built there. That's a giant wave up on the Ottawa River called Bussinger, which is pretty aptly named. And you can see some of the aerial kayaking moves that are possible on those real large wave features when you have really high water velocity. So we'll talk about some of the factors that are going to go into the successful design of these different wave features. And then we can kind of turn you guys loose with some questions on what we might be able to change in terms of our parameters and variables to arrive at a quality wave experience. Here's again is that wave in Munich, the ice block wave. You can see it's nearly a head-high wave being produced with about 3 feet of drop and about 600 CFS. So very similar in size and design of what we're proposing to do here on the sheet. So if we're lucky at the end of the day, we're going to have something that's going to be at least as good as that wave in Munich, and hopefully even taller and bigger. But that's the challenge to the engineers, and also a challenge for you guys to simulate and model it. All right, so that kind of concludes our slideshow there.
You want to use the board, Jason?
Yeah, can we do that? You guys have any questions at this time about that? I know we've kind of covered a broad swath of different topics. Hopefully some of those images will give you some inspiration for what might be possible there. I want to talk about one thing with modeling. First off, there's this notion of similitude. So I was really excited when the engineering group decided to take up this challenge of creating some different models, and hopefully it'll create inspiration in the community. Hopefully what you guys come up with will be inspiring to people that are wondering, what's going to happen here in the Deschutes River, and hopefully it'll also give some inspiration to the engineers and give them insight into some of the different approaches that you might come across to make the biggest possible wave. How it's going to be graded as far as qualitative determination, like if we're going to say, well, hey, Bend High is the winner this year, as we'd like you guys to be again. We're going to have an expert group of 3 different surfers. They're going to kind of take a look at this thing. But in general, I can just tell you that the taller the wave is, the wider it is, and the more green sort of open face it has, the better it's going to be. And you can actually model these things fairly accurately at the scale that we're going to be doing it. But what you should understand is that you can't completely accurately model something as complex as water using a small scale model like this. And the notion of that is called similitude. And basically what it's referring to is the fact that different forces, different effects, especially water viscosity, do not scale really well. So you can't control all those factors in your modeling. To do a model that would work perfectly at scale, that we could scale up to 1-to-1, or physical scale size, we would have to change the viscosity of the water. So because we're using water to model water, and we're using a reduced scale, the viscosity of water at that scale is going to be different. So we might have we might be able to come to some generalized conclusions as to how our different sections, our different slopes, our different undulations might create waves of different sizes, but it's not going to tell us exactly hey, if we just do this, it'll look exactly like that in the final result, in the full physical scale model. But what it will do is it'll give us a good notion of, if we control these parameters in different ways, what can we expect to see in a large scale situation. And that should give potentially some inspiration to the engineers who are looking at a bunch of different ways to come about in the design of this wave. And so hopefully what we'll see at the end of the day is that you guys will give some inspiration to the engineers to go out of their comfort zone. They're not very used to designing waves like this, and hopefully these physical models will give them some inspiration as to which direction to pursue in the design, the final design that we're going to employ in the surf park. So I'm really excited that you guys are getting an opportunity to basically do a scale model run at what is going to be ultimately a multi-million-dollar project. So I think that's pretty exciting, and hopefully you guys see it that way too. Let's just talk about a couple of the different factors that go into influencing design. I think there are probably 4 primary things that we can talk about that you guys may have some understanding of already. The first one is this cross-section. So the cross-section of the flow. You know, you guys can probably imagine if we narrow the flow, it gets faster. The wider it is, therefore the depth becomes less. As I imagine Gavin's talked to you guys a little bit about that. So that's the first thing that I would look at in terms of like the overall construction of your model. You know, we're going to have a tank that's going to basically be having water flowing over it with maybe some interchangeable, you know, structures that we can put in place. So, you know, if we imagine that we have a tank that's got vertical walls and we're going to have water flowing through it, if our section is, you know, sort of this shape, right, it's going to be very different than if we have a section, you know, that is real broad. Like if we have something that's more like this, right, we can expect that the water is going to be a lot thinner and maybe be flowing more slowly, right? So that would be probably the first thing that I would play with if I was you guys in terms of, you know, trying to understand like how do we create the most velocity given the constraints of the amount of water that we're using. That's a constant, right? If we know that all the teams are going to get, say, 1/3 of 1 CFS, whatever our fractional CFS is, that's going to be a constant throughout the competition, right? So we want to look at what we can influence, what kind of variables we can bring into play to create these different waveforms. And I think that the channel section is probably the first place that you guys should make investigation. And you can do this even in the absence of the final model using something as simple as a garden hose. You guys can go out and turn the hose on and run it through these different sections. And given the same constant for the gradient, you can also see whether or not the water velocity, and it should be visual. Of course, there are ways to measure that, of course. You can put a drop of dye in the water and see how long it takes it to travel a certain distance. But you guys could make a pretty quick investigation as to whether or not you know, a trapezoidal section, a rounded section maybe, might give you more velocity. And then also how this is going to interact with the water downstream in the pool is going to be kind of an interesting part of the experiment. One of the sections that I saw proposed by the engineers, so if we were to just, you know, chop it vertically and not try to do any sort of a perspective on it, one of the sections I saw proposed by the engineers was kind of interesting. It looked like this, where it had a lower section on the side. And I don't really understand exactly what they were thinking with that, but that was one of their proposals. And my hunch about this is that creating more water depth here on the sides creates more velocity. They're trying to come up with a certain shape that which, when it interacts with the pool below, is going to do something to make the wave stand up a little higher. So I think this would be something to investigate as well, if you guys have a way of doing even a really small scale model of this before we get to our actual flow tanks. And I'm not sure what the timeline for getting a flow tank.
Flow tank should be here late next week, and then we'll have about a week to play with it.
Okay. So you guys can maybe, you know, do some online investigation. You might be able to look and see if there's other examples of other whitewater parks that you see that are dried up that you can kind of use as examples. But I think that if we're going to look at these model sections, you know, controlling this width and narrowing it up obviously generally is going to make things faster. And that's something that you want if you're going to try to build a really fast, steep wave. That's what we want in the surfing experience. The next thing I think I would investigate would be this notion of undulation. Because we have our constants are going to be basically the amount of water in the system and the amount of head or gradient that we have, right? So how we distribute that gradient, I think, is going to be something that's going to really affect what the waveform is going to look like. So imagine we have our pool above, right? And we have our section, which is going to be projected along some sort of slope. Our water is going to flow over it like this, and then hopefully make our big wave here below below the, in the invert section of our pool, all right? This is typically what we see, that there's some sort of slight invert where if we're looking at the elevation now of our entire waveform, normally we have the head height is measured from here to here. Okay, so we have a constant there. That's going to be 2.5 to 3 feet of head height for this one drop. I know it doesn't sound like a whole lot, but there's a lot we can do. If we make this ramp a lot flatter, or if we make it steeper with the same constant, it's going to change significantly what this waveform downstream is going to look like. Okay, so that's something else that I think I would make an investigation of and try to come to some determination as to how do you milk the most speed of your water? How do you get potential energy, the head height, turned into kinetic energy? Does that sound reasonable? There's one other thing you can do with this that I think would be really interesting, and that is this notion of undulation. So these sloping ramps are pretty common in most waves that you see out in the river. Almost any time you're out in the river kayaking or surfing or whatever, if you find a wave that's surfable, there's generally some sort of sloping ramp upstream. But there's also one other thing that's usually present in those types of situations, and that is the presence of other waves that are interacting in the series, creating typically what we would call an undulation. So the waveform starts upstream and it builds because it's going through a couple of different magnifications. There's basically like an amplification that's happening of these small waveforms. So these sloping ramps generally have small stair steps in them. And this is common in like sandstone and other types of rock formation, where you might have the pool. So our sloped ramp may actually have some small steps in it going down, and these steps could also be projected above our sloped ramp as well. That's the way I've seen these waves built at theme parks like Dollywood and some places like that. If you've ever done any of those log rides, you guys been there, and you got a really thin sheet of water, and they're able to build these enormous waves in those rides. And the way they do that is this undulation and amplification effect. So what happens is the water that's flowing over it drops a little bit, drops again, and by the time it gets to the invert and the pool below, what you've got is a periodic waveform that's been set up by the drops or by the little bumps that they have, and it creates amplification of that waveform. So every time it drops again, it keeps getting bigger and bigger, so long as those drops are in some sort of periodic fashion. So the period, you guys remember from like mathematics and from physics, it would be the distance between either one of the trough to trough or peak to peak, right? So that's the period of the wave. And then we've got the amplitude here, So what's happening is as this drops down this ramp and it's flowing up and down, it's creating more amplification at that periodic waveform. So controlling that length, the period of the wave, as well as these little amplifiers, is I think a way to create undulation in the waveform rather than just having a smooth ramp with water coming straight down. I think that's a way that you can build a potentially much higher overall waveform down in your invert pool that's going to give you a much higher quality surf wave than just having a straight sloped ramp. And I only say this because in just about every good quality wave that's out in the river, you see these undulations happening upstream. So there's very few waves out in the river where you have just a straight sloping ramp coming into the waveform. It's almost always got some sort of undulation upstream from it, and that helps create the height of the wave. So I think that's something that I would really look at. Even if you were to take this straight sloped ramp like we have here, playing with these different angles, you can start playing with where to put in some of these little speed bumps to create an undulating flow that then is going to amplify the height, hopefully, of our wave here. So that's undulation, and I would definitely like to make an investigation of how that might play into your design. The last thing that I think I would play with, if we can imagine this water flowing down this way, so water's flowing down our ramp, and maybe we've got some undulation in it, and it's flowing into our invert at the bottom, the width here below the actual constriction that's creating our hydraulic jump is filled with an eddy. So you guys are kind of familiar with that? You guys know what I'm talking about? With the eddy. So that's like on the side of the river. Typically there'll be a spot where the water's often flowing upstream actually. So the water that's caught down here flows back up and it comes and pinches in, usually, excuse me, it pinches off the water that's flowing up in the eddy systems comes upstream and it pinches off and creates an interactive lateral wave. And that creates this sort of curling effect here that is then pushing the water towards the middle of the river. How these interactive laterals interface with the green water that's coming downstream into the wave has a huge effect on what the wave looks like. And there's an easy way for you guys to control that, and that's through the placement of small like control fins or flippers on the outside of the channel section. You can put like a small bump here or a small ramp. And I don't know if you guys know this or have heard that there are surf waves out in the irrigation canals that people ride on surfboards illegally. I probably shouldn't tell you that, but there are a bunch of them out there. And primarily they're being built only through the placement of these little ramps here, which are creating control of those laterals and their interaction with the green water that's going downstream. So these little like ramps basically can affect the shape of that lateral and the interaction with the eddy system below. And that has a huge effect on whether the wave actually stands up really tall or whether it's just like a real flat, fast undulation. So that's something else that I think is really worth investigating once you guys get your flow tank there. And you can make in the scale, you could probably use like popsicle sticks and just put like a pivot, like a pencil or something that you glue to it so that you can then change the shape of those laterals, almost like a ping pong, or not ping pong, but a pinball flipper, something like that. So just with the change of the cross section and those flippers, you can make a huge amount of change in the shape of the wave, right? So those are the primary areas that I think I would investigate if I were you, just from my perspective as a kayaker and from having seen some of these other surf parks designed. And I think that if you guys make investigation of those variables, I think you'll very quickly come to discover like what actually works to build these waves. Do you have any other questions about that or about these other ideas that we might try?
So maybe you take a minute and describe, I know we went through the slideshow a little bit, but what is ideal, and is there a different kind of wave for a different kind of discipline of recreational user?
Yeah, I think that's a great point, Kevin. Yeah, there definitely are. What we're hoping to see, for our wave park is something that's rideable by both surfboards as well as kayaks. And so, the more advanced rider, might want something which looks like this, where you have a hollow tubing section. But you can kind of see that for your average recreational rider, you're going to end up in here in the washing machine part of the wave. So, this would be great if, you could build something like this where you could actually get tubed or barreled on the Deschutes River. This would be an amazing thing for the very advanced surfer, but maybe not so great for your average recreational kayaker. I think that if we were to scroll through my photos here, this is an example of something that's really geared towards the novice or intermediate kayaker, where our wave here is maybe only like a foot tall, right? So what we're hoping to see is actually something that's really geared towards the expert kayakers and wave surfers, something that's really going to be inspiring to bring people from all over the country to come here and surf. And what we want to see in those types of features is a really steep face, when possible. In this wave, for example, what's actually happened is the entire waveform is broken back on itself. And so you have all this hydraulic foam pile here, which is great for kayaking, but this wouldn't be a very good recreational surfing experience because the green, usable face of the wave is quite flat and there's very little of it. So what we'd really like to see is a lot more green face with foam only at the top of the wave. Yeah?
So we were simulating waves earlier, and we could get a wave like that where it had a light of the foam and everything, and
Yep.
we could get a stable wave with lots of foam. We were having issues where when we tried to curve it though, it would end up collapsing in on itself
Yep.
after a little bit. would the only way to make it more stable is to improve the flow, or is there a way to make it more stable?
Yeah, so that collapse is probably being influenced by the pool depth downstream. So if that pool is filling with water, it could end up flooding over and changing the depth of that invert.
So if further downstream something is changing due to the amount of flow, that's going to affect it more than anything.
Absolutely. So in most wave systems, what you see is that the water downstream is flowing away as well. So if you have too much pool, if it's flowing into a real static pool and the water, there's no downstream velocity, you typically will not have waves. So that's a correlation between something called the Froude number, which is a mathematical term to describe the amount of energy that's contained in that wave system. And without getting too far into the actual hydrology of it, in general, to create hydraulic jumps that are stable green waves, you have to have a Froude number in excess of 2, which basically signifies how much energy is in the system. So you have to have a very high energy system, in other words, a lot of velocity coming down, but you can't be going into a real, just a real static pool. An example of that is if you have a real steep ramp, you might have a lot of energy coming in, but then it just creates a real steep hydraulic. All the energy is being dissipated in one spot, and it's a big foam pile. And those are actually like the real deadly type of hydraulics that you don't want to see below dams anymore. It used to be a really common thing to build in dams, but then if the water got high and someone got swept into it, they could drown and become stuck in that area. So those might have a really high Froude number as well, but it's not the qualitative experience we're looking for. So as far as how to control that and keep that waveform stable and open, you definitely need that water to flow downstream away from it. It can't just be flowing into the static pool. So if I was building my model, I wouldn't want the recirculating pool at the bottom. I wouldn't want my model submerged in that pool. It has to be above and then angle the outflow of your modeled area away from that, down into that pool. Does that make sense? And that's what we're going to see here in our Colorado Dam experience too, right? Because the primary pool here, the primary pool here is flowing, water's flowing away into the other pools downstream. So that's a good question, because that's going to be one of the challenges for sure. So in looking at that, if you're looking at your elevation sections, if we have our primary pool here, our sloped ramp, our invert, this pool is going to flow downhill again away, and then to our next hydraulic drop and jump. So that is a necessary component, and affecting this pitch and angle of your outflowing water is going to be crucial in getting a stable waveform. Absolutely, I think that's a really critical insight. So you guys have done some modeling already. You've played around with this a little bit. It's great. This is something you can do very easily in the river too. You can go down to any place with flowing water and create these models pretty easily. You can go, just divert a little bit of water on the side. If you build some rocks and run it through and make your own sluice box. And you can run a lot of these experiments if you make the little cross sections. You guys can take like just a block of wood, like a 2x4, cut it on a bandsaw to create your section there and play with the pitch. Obviously, the bigger the scale is, the more discernible the qualitative aspects of your wave creations are going to be. Right? So the larger scale helps a bunch. When you get to a certain small scale, the viscosity is so different on water, at real small scale as opposed to large scale, that it really doesn't translate very well. And that's the nature of similitude. And that was one of the terms that I thought I'd bring up that you guys could investigate if you're curious about hydrology in a greater way. Other questions about the wave quality that we were just talking about?
Jayson, what would be a good way to approach this with just the design of wave number 1 or all 3 waves? Or
I would just concentrate really on wave number 1, understanding that you're in your model, you're going to definitely need to have that water flowing away. However, that being said, if you guys, and I'm sure the model provides enough vertical head, 8 feet is what we have to work with the Colorado Dam, and we're going to get 4 features out of that. So I think when you look at how much depth is, or how much drop is possible in your model, you could easily, should you want to, try to simulate different waves along different drops. And that might actually speed your modeling process, because you can try different shapes at each of the different drops. Does that make sense? But what I would do, probably for the sake of modeling, is keep your overall drop consistent to 2.5 to 3 feet between each of the different drops, so that you're basically simulating the same amount of potential energy for the water that's dropping through there. But that would allow you to play with things like the pitch of the ramp, the undulations maybe in the profile, things like that that you might want to experiment with to create a more stable waveform, a bigger overall wave. Other questions? You guys excited at all for this? Does it sound fun? Does it sound like an interesting challenge?
Yeah.
Pretty different than anything else we've done so far in technology class, I imagine? Yeah. Okay, well, hopefully you guys will get wet doing this, hopefully you get inspired, and hopefully at the end of this, what we'll do is we'll actually come to some discovery as to how to build these waves in a fashion that will actually inspire our engineers to maybe look at some of the actual processes you guys went through in their virtual design of the waves that we're actually going to build at Colorado Dam. Because I think that we're definitely getting them out of their comfort zone. They like building hydraulics. They like building stuff that looks like this. That's their comfort zone. You know, the greener faces are definitely not as common in most of the parks here in the U.S. Again, here's that wave in Munich that I think is worth looking at. It's called the Eisbach, E-I-S-B-A-C-H. It's a great spot. If you guys ever go over to Oktoberfest, I definitely recommend a trip to the top of the English Garden, which is where that wave is. Pretty easy to find. The English Garden is a pretty famous spot too for nude sunbathing, so that's also with a visit on its own. Yeah, exactly. Here, you guys are asking about these lateral waves. There's not a whole lot of eddy actually behind this wave in the Eisbach, but you can kind of see the laterals here interacting with the wave shape itself. One of the unique features of the Eisbach wave is in the sloping ramp, there is something that they placed in there, which is a tunable plate. So the angle of this plate is tunable. And this is something else you might want to check out and play with. They have a pivot there, and this plate can be elevated or declined. The declination angle can be played with. And what is happening here is the water flowing down. Again, we're getting an undulation as a result of it coming off this ramp. And that tunability there of that plate is doing a lot to create that waveform. Interesting story, years ago, this is a power canal, and they have somebody that's placed in charge, sort of like a ditch rider here on our irrigation canals. His job is to prevent this structure from turning into a huge hydraulic, which would then scour the footings and erode the road. There's a road on one side of this, and to prevent the canal from being piped or eroded. And so they put that tuned plate design in there to make sure that this waveform stays as a constant sort of wave rather than turning into a big hydraulic, which is going to do more scouring. And they kept finding that the lock that controlled the elevator screw on the tuned plate was always cut off. And at first the guy was not sure who was doing it or why. And he pretty quickly came to the realization that the surfers were doing it and setting it up as a wave. And in a very different sort of fashion than what we would have here in the U.S., where there would be lawsuits and no trespassing signs put up, the irrigation or the canal company came to an agreement with the local surf club and put them in charge of tuning the plate. So as long as they had the understanding that it was to be maintained as a green wave, which is what the surfers wanted anyway. So the surfers are now in charge of the actual tuning of this feature, but they are able through this tuned plate, through changing the inclination or declination of the plate, they're able to influence both the period of the wave, so the length here, our period, and they're also able to influence the undulation, and that both those factors help with the placement of the wave in the trough of our invert, which in turn influences the steepness of the face. And what we want is we want the steepest, tallest face with foam pile at the top, but we don't want big foam piles coming all the way down the wave face. So that's really what we're looking for. And if you guys want a picture of like a wave that I think would be, this is a great wave for surfing, absolutely. There again, you can see the nice tall green face. It's probably like waist high in this photo. It changes in size and shape based upon the time of year and how much water is in the canal and how they set it up. Most of these are about waist high. That one's a little taller. That one's almost head high. That's pipeline wave on the Loxaw River up in Idaho. So if you had something that was that tall with the wave face, that would really be a great result. So if you had 2 or 3 feet of potential energy of drop, and you were able to produce a wave that was 5 feet tall or 6 feet tall, you'd really have a great result. Again, there's another view of bus heater on the Ottawa, and you can see that one's like 7 or 8 feet tall. And that's considered to be a really tall river wave. There's a guy crashing at lunch counter wave on the Snake River. There's another icebox photo. So if you wanted an idea of what would be like an ideal wave shape, this is pretty ideal. What we've got here is a big, big, broad face with foam pile here and kind of a diamond-shaped open face. That would pretty much be, like a world-class wave. That is a world-class wave. Anyway, if you could produce something of that shape, obviously it's not going to be to that scale. And it just shoots with 1,000 CFS. That's probably on the order of 60,000 CFS going through that channel on the Ottawa. Yeah, so in general, more water, better results. That's pretty obvious. But there's a lot you can do given the limited constraint of 1,000 CFS. And so we're hoping to maximize our performance of our wave at 1,000 CFS that we're roughly going to have going through the Whitewater Channel at the surf park. There's another picture of a pipeline on the Loxaw. Looks like a pretty fun time. And there's another shot of the icebox wave. You can see that in comparison to some of the other photos we had of it, it's considerably taller in this photo. So all that's just being influenced by probably the flow and the tune, like the way that they've tuned the plate. They've just got it set up a lot better in this photo than they do in some of the other photos. You can see that thing's probably about 4 feet tall. So that's a pretty good result with 600 CFS. It's a really fun spot. Yeah?
Do you think that plate they're using are having a curved or like a flat plate?
Oh, good question. I personally would tend to think that it would be better if it had some sort of curvature to mimic the undulation you're trying to create. And it could be quite long, if you want to think about the...
Yeah, if you got 1 second, go ahead.
Yeah.
Go ahead, finish up.
Okay. Yeah, I would look at this length and I would try to think about what you want for this wave length. I think that tuned plate should be half the period, roughly. So if you're thinking about a long trough with a steep wave, in general, the longer the trough, the steeper wave you can create. So if that's 10 to 15 feet in our physical model, this distance here, I would want that plate to be half the period. I think would be what you're going to want. So I would, in scale, I think that's 5 to 7 feet. So in your model, it may only be, a quarter of an inch or half an inch, but it'll make a big difference. Yeah, you could definitely play with the length of that. I would think that some sort of curvature to create that undulation would be a benefit.
Cool. Thank you very much.
Thank you.